In this video, I will explain you what is De-Broglie hypothesis. Okay, so far we have learned that radiations are associated with matter nature. Okay, and with a light radiation, the matter by which the light is made up of is called as photon. Okay, so De-Broglie has told that if radiation is associated with a matter nature, then the matter will be associated with a wave nature. Okay, so this is radiation, this has a matter nature associated with it. So any object which is moving, that will have a wave nature associated with it. For example, whenever electrons are moving, then there will be a wave associated with it. Now whenever there is a wave, there will be a wavelength associated with, right? So that is the basic property or basic parameter on which a wave is evaluated. What is wavelength? This is a wavelength. This is a wavelength. This is another wavelength. Now De-Broglie has called this wave as matter wave. Don't confuse matter wave with material wave. Material wave is different. Whenever we are speaking, now see, our speech is basically compressing the air molecules here. Now these air molecules will be compressed, then rarefaction, compression, rarefaction. So these are material waves. This will be propagated through a medium. Okay, so that is due to vibration of particles. And we have learned about radiation as well. So these are called as matter wave. This is associated with a moving matter. Moving matter in the sense any object which is materialistic in nature, due to moving of that object, there will be a wavelength associated with it. And those are matter wave. For example, a moving car will be associated with moving car, moving bus, moving elephant, moving electron. So these all objects will be associated with a wave. Now De-Broglie has given the wavelength of wave associated with a moving object, which is equal to h by p, where h is the Planck's constant and p is the momentum of the moving particle. Now with an object, with a material, with a matter, what is the momentum? That is equal to m into v, because matter is having a mass, so momentum will be m into v. But in the case of radiation, that will be just h by p, where we can't equate p as mv with radiation, but with matter I can rewrite momentum as m into v, because matter is having a mass and on moving it will be associated with the velocity. So h by mv is the wavelength associated with a moving object. Now how will this wavelength be dependent on temperature? Will the wavelength change with temperature? We will see that. Okay, now we know that the kinetic energy of molecules as a function of temperature. Last year we have learned that kinetic energy of molecule, which is equal to half mv square. This is kinetic energy, and the value is equal to 3 by 2 kT, where K is the Boltzmann's constant and T is the absolute temperature. We need mv to substitute here, but we have mv square here. Now how to get mv? Then this is equal to 3 by 2 kT is equal to half mv square into, I will multiply with m and divide with m. So it is simply multiplying with 1, the equation will not change. So I am multiplying and dividing with m, so that this equation will become m square v square divided by 2m. Now these two and this two will cancel, so that I will get m square v square is equal to 3m kt. So from here mv is equal to square root of this, root of 3m kt. Now this value I can substitute here, so that I can equate h by mv as h by, instead of m, v root of 3m kt. This is a very important relation. Okay, now when temperature is increasing, the wavelength will decrease. Okay, thank you.